Welcome engineering statics students. This is ENGR ampersand 214 at Bellingham Technical College. And in this lecture we'll be discussing special force systems. This is basically a vocabulary exercise where you learn words that basically denote the orientation of forces and moments in a given force system. These types of force systems generally have special properties that really simplify analysis. So they're often referred to by these names, and you can take these names and then their definitions and be able to know, what their lines of actions and significance are from an analysis standpoint. So let's start with concurrent. In a concurrent force system, the lines of action of all the forces pass through a single point. So you can think of maybe a grommet or some kind of single point to which a bunch of ropes are tied. Each of those ropes is going to have a line of force that's oriented along its line of direction. It's all in tension. All of them come together at a single point, and as a result, here's the significance: no moments can be generated about the point where all of the forces converge. So there's no torque exerted by the forces. Okay, so you can have a net force if they're not balanced, if the sum in two orthogonal directions or three orthogonal directions is not zero, but you won't have a moment. Okay. The next next step up in complexity is coplanar, and in this system all of the forces have lines of action which lie in the same plane. So obviously if you have two forces, they'll have lines of action that define a plane. So of course they're going to lie in the same plane because they define it. But if you have a third force in the system, it would have to lie in the same plane as the other two, or however many you have. A second requirement is that all of the couples that might be present in the system are oriented such that they are perpendicular to that plane. So given that all of the forces are in a single plane, the moments that they generate about a point in that plane are by definition also going to be perpendicular to the plane, just by our cross product rule. So if we've already constrained all of the couple moments to be perpendicular to the plane, it means all of the moments in the system are perpendicular to the plane that the forces sit in. So that kind of restricts the amount of directions in which we can have twisting, flexion in the system. We can have only one direction of flexion. We can have all twisting and no flexion, that kind of thing. So that simplifies the system in terms of applications. So that's coplanar. Forces in the same plane, couples perpendicular to that plane. Parallel. This is pretty simple. The lines of action of all the forces are parallel. And distributed loads are probably the biggest population in this category. So things like the force of gravity or hydraulics, hydrostatics, pneumatics, where we have pressure. Those are distributed loads, and so the line of action of the net force of the distributed forces, they're all parallel, typically to the surface on which they act. So that's an example of parallel. In terms of something that literally can replace anything, the force resultant with additional moment, that is producing a twist around the line of action of the force. This is called a collinear force couple system, or equipolant screwdriver, because this is kind of what a screwdriver does. If you push down with your screwdriver onto the head to make sure it stays engaged and then twist it, that's the type of force you're applying here. So you can use this kind of equipolant system, this collinear force couple system, to replace any force system. So any kind of force system, we can get the sum of the forces and have a direction and magnitude somewhere in 3D space, and then have a single moment that is the result of all of the applied couples and all of the forces about a given point. So we'll go through that kind of exercise in conditions of equilibrium, but this is one simplifying tool that we can use. If we have a bunch of forces and applied couples, we can basically condense them all down into this single equipolant screwdriver, and then use that to determine if something will accelerate. If nothing's opposing it, it will. So just as a last note here, because this is a good segue into our next section on distributed loads, here's a typical example of a parallel force system that's taking the form of a distributed load. In this little figure we've got a beam, and it can rotate about a pivot point here on the left, and it can rotate about a pivot point on the right, and it's also on rollers, and this is symbolizing a bearing that is not constrained in the y direction and the vertical direction, so or in the x direction. So it can't sink down, but it can float up, and it can move side to side. And we have a distributed load, usually denoted by Q, which is a function of where you are on the beam. So this could be maybe like a tank or a container of gravel where the pile is really high over at this point, and there's none over here. It's an uneven load, and so the weight of that, the pounds per linear foot, is much higher here than it is over here. So if we wanted to get a single force resultant and positioned properly that would represent the action of this distributed load, we would be getting a force resultant for a parallel system. And I'm going to walk you through just really quickly how we would do that, because there's not too many equations here. We'll do this in much more detail when we look particularly at distributed loads and equivalent force resultants. So the way we go about this is we use a continuous function of horizontal distance from a given reference point to represent this. So we have to turn this into a mathematical expression. So we get an expression Q as a function of x, and x being the position along this beam. And we make, this is a linear function obviously, it's 0 when x is 0, and it's 10 pounds per foot when x is 6 feet, and so basically that's a line going through the origin. And so we use rise over run for our slope. Basically 10 pounds per foot divided by 6 feet is the slope, rise over run, and so we can simplify that down to 5/3 pounds per square foot times x. It's a line function. So when x equals 6 feet, we have 30 divided by 3, or 10 pounds per foot, and when x equals 0, this is equal to 0. If we want to get an equivalent downward force from this, all we have to do is sum this up over all the x's over which it operates. And this is where we start pulling out our integral calculus, because that's the best and easiest way to sum something up over continuously over a distance. So in this case, we would just take our distributed load and we would add up its effects from over all the x's where it operates. So we'd start at 0 and we'd integrate up to 6 feet with respect to x, our horizontal distance. So we basically have the integral from 0 to 6 feet of 5/3 pounds per square foot x. When we take the integral of a polynomial, we basically get the next power up, and then we have a 1/2. What we've done is we found the function for which, if we took the derivative with respect to x, we'd get this. That's the definition of integrals, basically. And this is a definite integral. We're going to integrate over limits. So we have our integrated function, and then we plug in the 6 feet, evaluate it, and then plug in the 0 feet and evaluate it, subtract the 2, and we end up with 30 pounds. Because this is a line function, we can also use the other property of integrals, which is the area under the curve that this function would form as kind of a graph. And so we can also use the area of a triangle to get that too. This is simple. If we had a more complicated function, a sine wave or a parabola or heavens knows what, which you might have, you're going to have to end up using some calculus or numerical techniques to evaluate it. A lot of times you'll have distributed loads that are due to weight, and so unless you have a very complicated structure, quite often you won't have to integrate. You'll have a straight line, so the area under it's like a rectangle, so that's pretty easy. But the point is, you get the resultant total downward force that's the result of this parallel force system acting, and so it's 30 pounds. So the next step is, where do I put it? Is it acting right here? Is it acting back there? Is it acting halfway between? Well, if I want it to be equivalent, my next consideration when I think of an equivalent force system, it has to produce the same net force, which we just accomplished, but it also has to produce the same moment about a given point in the system. So if I were to take the moment of this distributed load around, say, the origin, pretty easy to do, then I could basically use my definition of moment with a perpendicular system, and I would know how far out from point A I would have to place that F sub r, the force resultant, to get the same torque, the same moment about point A. So the way we calculate moment for a distributed function is to take our distributed load times the distance at which it's being applied. So that's kind of the definition of moment in here, but it's applied to just a little piece of this load. And then, so we're basically applying that that principle of moments, that the moment of the sum is equal to the sum of the moments. This expression here, m sub r, is a continuous sum of a whole bunch of little bitty moments. So we're using an integral from calculus to sum a whole bunch of moments. So this expression q sub x times x is a little bitty moment due to an infinitesimal slice of this distributed load at a given radius from point A. So the moment of the sum is just, here's our force sum, we're going to put it at a single place. So this is just an integral enabled way of applying the definition of moments to a continuous distributed load. So I can basically drop this same expression in here, plop it right in there, and of course I have another x multiplier, so my integral is a little bit different. I have a squared term, and so when I integrate it I end up with a cubic term. And then I evaluate between my limits and I end up with 120 foot-pounds, which is great because it's the right units. So in order to achieve 120 foot-pounds of torque or moment from a 30-pound load, it better be at 4 feet from the turning point, from the point around which I'm calculating the moment. So I'm going to have to put F sub r right out here at 4 feet. And this is the moment of the sum is equal to the integrated sum of the moments. So you'll be practicing doing that quite a bit, and this will be quite the key to calculating a shear and bending moment later on when we take one of these simple beams and we start understanding what's going on internally and looking at internal loading. So this is the setup for doing that, and that's a very important type of calculation that you'll very likely do as mechanical or civil engineers, whichever path you go. So that is it for special force systems. We spent a whole lot of time with the distributed load, which is a parallel force system. We went over the concept of the equipollent screwdriver and the note that any system of forces can be replaced with a single force and a moment that turns about its line of action. Coplanar, forces all in the same plane, couple moments perpendicular to the plane. Concurrent, all the lines of action go through the single point, no resultant moment about that point. And so we are now ready to dive into a more in-depth discussion of this type of resultant force due to a distributed load next time.